Hey, John here. Let's talk about programmable logic devices. As always, thank you to my Patreons. You help a lot. I really appreciate it, especially the VIPs. So here's a Wikipedia page. I use Wikipedia because they let you freely share their stuff in places like this as long as you cite your source. Thank you very much, Wikipedia. Now, what's the downside of Wikipedia? They themselves observe that this introduction may be a little bit short to adequately summarize the key points, and that is true. However, they have a nice diagram right here, and what they say is not false. It just might be a little bit brief, okay, as they say. Where are we? Okay, so where I'm heading with this is I want to talk about FPGAs. But before we do that, let's look a little bit about where they came from and why they exist and kind of how they relate to other logic devices. If you've never used any of these, you might be, running around asking, how come we don't do this or how come we don't do that? Well, here's why, okay? So you've got a couple of different types of programmable logic devices. And down here they outline them. There's simple programmable logic devices, complex programmable logic devices, and field programmable gate arrays, which is funny because field programmable gate arrays act a lot like not having any actual gates in them, and these up here that don't have the word gate in their name are actually made out of gates. So what little side note there, I find that mildly humorous. Moving on. Okay, so what you have here is a diagram of the innards of a programmable array logic device, a PAL. A PAL means this kind of a circuit right here, which is, as they say, is a sum of products logic array. Now, I'm going to include some links to this video to some college lectures that I gave on Boolean algebra and how to apply it and what the sum of products, product of sum, and De Morgan's theorems and all that other fun stuff mean. So if you lose track in here, when I assert something as true, you can click on the links in the description below this video and look at the college lectures on what a sum of product array is and why we care about them and how they relate to other things, okay? I'm not going to repeat all that in here. Okay, so you've got these three classes of devices. They start, oddly enough, with a PLA, which is even simpler than this diagram here, but it kind of came and went fairly quickly. And the PAL is the thing that, if you were around back in those days, that's kind of what you remember. Well, you'd have to be older than me to remember the PLA, all right? I was 8, I don't know, maybe, when that was had its heyday. So to me, the PAL was the thing when I was in high school and college, and then the others came later. So speaking of college lectures, here's some slides I found from Dr. Wang here at Southern Illinois University. I wish this had a date on it because it feels a little bit dated when I flip through here. But the reason I want to look at this is it's only 8 or 9 pages, and it really addresses the issue closely here. He should have titled this thing PAL, CPLD, and FPGA because he talks about all of them in here. And these diagrams are a little better. This is a better introduction. This is the introduction that Wikipedia probably wishes that they had, is my point here, right? So he refers to these as field programmable devices, while Wikipedia called these programmable. And again, a little terminology thing in here. But they mean the same thing. And here's the date I was looking for. So this is 25 years old. And yes, it kind of feels that way to me because of the numbers that they put in here. FPGAs today are vastly larger than some of the numbers that you see at the end of this particular handout. Okay, so what is he talking about? These things are integrated circuits that you can program And by programming, they mean that the consumer, the person that buys the chip, can program it. In other words, it doesn't have to be programmed by the manufacturer. I don't have to ask the manufacturer to make me a custom chip, sometimes called an ASIC, which stands for Application Specific Integrated Circuit. I can order one of these things, and then I can tailor it to my specific needs. And that's what they really mean when they say field programmable, right? The consumer, being the person that buys the chips, can program the thing. Now, here's the main reason I chose this particular handout. On one page, he's got all these things in here. Again, terminology. I don't want you to get disoriented if you're really new to this stuff. PLAs, this is your 50-year-old stuff. And what you have here is these are small because back in those days, you couldn't put a lot on one piece of silicon. These things had what they call a programmable AND plane and a programmable OR plane, right? The PAL, which is the common name you hear a lot of these days, has a programmable AND plane and a OR plane that is not programmable. This gets us back to our sum of products, and we'll look at that very briefly, and then I'll pass that off to another recording that I did some years ago if you need more detail on what this all means, why we care about AND planes and OR planes when we are talking about these particular chips. The takeaway right now is that these are more configurable because you can program both the AND and the OR functions, while this is less programmable. But as you could imagine, if it has less functionality, it's cheaper. This thing is a very popular device, and you can still buy them today. These are not so much so, presumably because they cost a lot of money in 1971 and were more primitive than these uber fancy PALs that came out in the end of the 70s. And because they were less expensive, they're very appealing to manufacturers and stuff like that. So these became a big player in the early 80s. You couldn't buy a circuit board that didn't have one of these things hiding on it somewhere. And the value, as we'll see in a minute, is that you can take one of these and replace an enormous number of TTL gates, like 7400s or 4000 series gates on chips. You could have dozens of those chips on a board and take all that away and replace it with one single PAL. Okay, and we'll talk a little bit about why in a minute. Okay, so the simple PLDs are either a PLA or a PAL. So these are the class of simple ones, right? These two guys up here, these so-called AND plane and OR planes that you can program together, right? A CPLD, as they point out, is a bit more complex than a PLD, or the simple ones. And the idea is, with this, in the simplest of terms, okay, we want to get to the good stuff, is that this acts as if there are a large number, or multiple, a plurality, I should say, of these PAL devices all on one chip. And as we'll see in a diagram below, there's a way to connect them all together. So there's routing, we say, as well as these programmable arrays. And FPGA, on the other hand, in oversimplified terms, is a more generalized structure. That is absolutely true than these than the CPLDs and the PALs and so on. And it allows you to have a very high logic capacity. And we'll see why that's true in a few minutes, okay? Let's look at the PLA. Well, this is a very stylized schematic. The way you look at this, if you're not familiar with this type of drawing, is that you have an AND gate here with multiple inputs. One of the inputs goes to this vertical line, another input goes to this vertical line, another input goes to this vertical line, and so on. Okay? And these represent fuses that you saw on the Wikipedia page that you can remove. The idea is you can connect, in this example, 4 inputs on this AND gate to each of these vertical lines as many as you want. Now, if you're paying attention, you would notice that if I hook the input of an AND gate to this vertical line and another input to this vertical line over here, and these two come together through an inverter like this can never be both true at the same time. Therefore, the output of that AND gate is always false. Okay? So when you program these things, you obviously got to pay attention. The idea is that you can take this AND gate and say when y is a 0, I want one of the inputs to be true. If I remove this fuse here, that input to this AND gate is assumed to always be true. So what you're really doing is removing the things you don't want to connect up to the input of this AND gate. And yes, they could be implemented as a wired AND or a wired OR. That's just merely an optimization of the silicon implementer. I'm not going to get into the details of that sort of thing, okay? Bottom line is that's an AND gate, and I can connect it up to as many of these vertical lines as I want to perform any function that I want to, given either whether y is true or false and so on. The output of each of these AND gates can be hooked up to these OR gates over here in a similar way. This is the programmable OR plane that you don't see in the PAL chips. The PLA, you can have fuses on the left and on the right. And therefore, I can take this OR gate and say, I want the output to be true when that AND gate is true, or when this one up here is true, if I remove these two fuses here, for example. Okay, that's how you would program this thing. And again, if you don't remember how sum of products and product of sums work, go look at the handouts and the other lectures that I'm going to link to below, where I explain how any Boolean function of any kind that is combinational could be implemented using this circuit. And that's the beauty. If I want to have a decoder, I can build a decoder. If I just want an AND function, I can have an AND. If I want a NAND or a NOR, or I want output 4 to be true when y is a 1 and x is a 0, and maybe there's other inputs over here, and this is an overly simplistic diagram. Usually there's a dozen or so inputs and 8 or so outputs on these types of devices. So you can use these for really fancy, I think of them as really fancy decoders, like a 74LS138, where you have the 3 inputs that decode into the 8 outputs, and I use those for address decoding. Okay, but you can have a real fancy version of that here, and each one of these outputs could be used to enable various I/O devices and things like that. Okay. So, what do we got here? This is a class lecture. So let's say it's programmed, and let's look at an example in here and say the X's are the connections and the open crossings have been disconnected, right? Well, in this case, we know this is X bar ANDed with Y bar ANDed with Z. And if you're not familiar with the notation, look at the video below. I talk about that as well. The AND function quite often can be drawn with juxtaposed letters like this. There's many different notations, and I wish people would, all use the same one. It's unfortunate that they don't, but that's one of the things you're going to have to deal with if you're going to Google around the internet and get free information. They're going to talk in their own notations. So what do we got in here? How does this work? Why is that true? Well, if you look at X over here, you'll see that the inverted version of X goes to this line into that AND gate, and the true version of X over here is not connected. So this is X bar right here, goes into the AND gate, so you're going to see it over there. Y, the inverted version of Y goes into that AND gate, and the true version does not, okay? And the true version of Z goes in there, and then the false version does not. So this is X bar ANDed with a Y bar ANDed with Z, and that will propagate out this OR gate here, and you can see that term, that product, as we say, coming out of this OR gate. But it's also connected to this other AND gate over here, which you can see is connected up such that this AND gate is true when X is 1 and Z is 0. And that also is connected to the OR gate, which is this term over there. So this is the OR gate being represented by the plus, okay? And the AND gate being represented in a lot of ways like a multiplication from grade school. If these were all, variables, you're summing products. Which brings us to the conclusion that this expression right here is the sum of these two products. And that's what they mean by a sum of products. OR gates look like adders. You might perform saturated arithmetic. I'll talk about that in a minute in a quick review in a second. I'll look at some handouts that I put together on that. Here's a PAL. As opposed to the PLA, I can only program this side over here. I cannot program the OR gates on this side. And the manufacturers pick a bunch of kind of configured standard sort of configurations over here. So this is less flexible, but cheaper, right? And what do we all want? Cheap electronics that go fast. So this is good enough. This one is the winner for a decade. This was what, and even today, you still see these on occasion, mostly in retro kind of projects, but these were hugely popular in their time, okay? Same thing, I can program these, and I have to pick which output is best suited for what kind of things I want to program over there, okay? That's all there is to it. Work it out. You can see how these things can be useful. What else do we got? Logic expanders. So over the years, they make these things more fancy, and sometimes the output of some of these gates can be fed back around to the inputs and so on. And because it's a class lecture, I'm sure the lecturer would stop and ask the student who can tell you what the function of this thing is. Notice this one is not connected at all. All right, I would argue the output is 1 because normally, when you do this, if you don't connect any of the inputs, these things are all considered true so that you can make use of these gates when you want to get rid of, when you program, you burn all the fuses out of here. What you're really doing is saying, I don't want to consider this input, and any unused input on an AND gate would be a problem for the rest of the logic if it went to 0, so it must go to 1. So in this case, I suspect this is a foolish program that would be 1. Prove me wrong, comments below. All right, so what are we going to do? Talk about the differences between the PLA and the PAL. PLAs are more flexible. But, as they point out, they're more expensive. And just due to the way they're built, at the time, they were slower than a PAL. All right, so you give up a little bit, but you gain something else back. That's always the rule, right? You can have it fast, good, or cheap. Pick 2. That's the only options you have. So they went with fast and cheap. What else do they got? You can also, combine multiple PALs together, but when you do that, then things start slowing down. Obviously, because they're daisy-chained together and they can propagate through the gates and on their merry way, which is also true if you're using discrete gates and they're all, sequentially connected together. So I'm not sure that this is how significant the word significant is in here. I've never tried that, so I can't speak to that. Anybody familiar with doing that sort of thing? I'd like to hear about it in the comments below. What were the super awesome circuits you guys would have made with multiple PALs back in the day? So what do we got? They also have the option to put a D flip-flop on the output of a PAL. And the idea with that is you can implement a sequential circuit instead of just a combinational one. By that, on the outputs, they mean down here. So there might be a D latch over here with a clock that would come in. So you could put, set a bunch of bits over here. Then the functions would settle down, and there'd be various ones and zeros over there. And you'd assert a clock, and it would latch on the value of these outputs, so the outputs would stay stable over the course of time, while these other input bits over here could be changing. And once you put a latch over here, you can then take the output of this latch and connect it to some other circuitry and or put it back into its own inputs. And once you do that, you can build a state machine. And the simplest state machine that I can think of and describe without drawing up any diagrams and stuff would be a counter. The next value of a counter depends on the current value. So if the current value is 0 and you clock it, it should go to 1. Or maybe it's counting in the other direction, but you know what I mean. If it's a 1 and you clock it again, it should go to a 2, and so on. And you could easily build a circuit using this with a latch right in here, and the output of that latch can come back around here, and you can analyze the current value of the counter. If you had 4 inputs, of course, if there were more, and they usually are, on a PAL. There's usually like 16 or 20 inputs on a PAL. Then these can decode the current value, and you can calculate the value that it should be next to come out of these OR gates so that on the next clock it counts up. And I'll put a link to my lecture where I talk about that if they're not familiar with how those work either, from my university days. Okay, now let's move on to the CPLD. As I said before, it looks a lot like you just got a whole bunch of PALs on one chip. I've never used these. I've used systems that have them in them. These are just really big PAL circuits, okay? And they have a programmable interconnect, which is pretty cool because obviously if I'm going to put multiple PALs on one chip, I would need a way to connect them together. If I'm going to put PALs on a circuit board, I might have, I put traces between the various chips so I can connect them together. How do you do it when they're all on one chip? Well, I need to be able to have it programmable. Otherwise, it becomes too close to a fixed function type of device. So when you program one of these, you not only say, hey, I want this PAL to do these functions, I want the outputs to be connected to this guy over here and so on. And these I/O blocks are usually how you connect to the pins, the physical pins of the chips. All right. So this is basically a bunch of PALs on one big chip. You may have heard of Altera and Xilinx. Altera has a Max line of CPLDs, and this is one of the example chip from one of their Max here. What does this say? This is like a 2000 or whatever, macrocell, blah, blah, blah. This is a 9000. Okay. All right, so this style of chip, what do they got in here? They draw a diagram. They say, here's all these LABs. Well, each one of these local arrays is going to be basically one of these PALs. And these macro cells are going to be represent the outputs of each of those PALs. And they have latches and stuff in here. So you can create state machines. And then they talk about this chip-wide interconnect, and then these things connect to the pins around the outside, okay? So he explodes open the macro cell over here, and you can see what's going on in here. We'll look much more closely at one of these that's on an FPGA, but they are very similar. So we're starting to see what is common in FPGAs in the Max CPLD here. And by that I mean the local array, as they call it over here, the outputs of this thing feed into, there's your latch, okay? And you can program the output. You can say, look, when the output comes over here and I'm summing up these products and stuff like that, I want to see the product, or I want it to go through a D-latch so that I can latch it and hold that output if I want to. I can also take that output and feed it back in. So there's my state machine right there, all inside one chip. Okay, so you don't have to then connect the outputs back around to the inputs on the chip itself if you don't want to. You can feed them back this way. What else have we got going in here? So there's a product term select. I'm not familiar with the Max. What does that thing do? What does it do? It says here's the clock clear preset enable system clock. So these are obviously here to control this latch. When do we want to latch the outputs? Under what conditions do you want to latch your output based on the logic that comes out of the programmable array over here? What's this thing? Programmable inversion. Well, sometimes, when you take the output, you want the opposite. You want to put it through a NOT gate. Well, an XOR gate like this, if the input over here is a 1, it will make this act as though it's inverting this input over here. So this is very common in FPGAs and CPLDs. So do you want the output to be true, or do you want it to have a bar over it? That's also usually programmable in these things. What has it got over here? It also connects down here somewhere else, parallel expander to the next macro cell, so that you can kind of tie these things together and you can do complicated functions. Even across all these output pins, okay? And this feedback inside here can either go directly from the combinational output or the latched version. if you're going to latch it in this D-latch. Depending on the vendors and the chip series, it might be that this line here is on the output pin like it's shown here, or it might go over here. I mean, this is all the different, this is why we have so many different options to buy the chips, different style of how you want to use the circuitry that you're buying, okay? Now, what has he got? I got a question down here. It has 33 inputs. Can you explain why the LA has 114 inputs? I suspect it's because 33 inputs, because of what we saw up here, turn into these guys. So these are your inputs down here. Each input has two lines that go into the programmable array up there, both the true and the false forms, okay? So if you have a chip that's got 33 inputs, it's going to have 66 lines coming up into this array. Now, they also say that you can take the output and feed it back around this way, all right? Presumably it has however many outputs times 3, which would take 66 and bring it up to 114. I wonder how many outputs this thing has. Oh, it has 16 macro cells. Therefore, it must have 16 outputs. And 16 times 3 plus 33 times 2, I'm going to guess, equals 114. I'll leave the prove me wrong in the comments below. That's probably the answer to that question. Moving on to the FPGA, which is where we want to be. Okay, so what's the logical evolution of all this? We've got these simple programmable blocks, and they were a godsend in the day. It got all the extra chips off the circuit boards. It allowed manufacturers to not tell you how anything works, too. So it's the beginning of the, oh no, it's proprietary, and I don't know how to reproduce this thing. You know, and that could be problematic, you know, if you're trying to clone a piece of hardware. Or it could be great if you're the manufacturer and you hide your super secret, super awesome logic on your Commodore 64 motherboard or something like that, right? But ultimately, and in the end, the average consumer wants cheap, fast gadgets. And that's what you get by eliminating the extra chips, reducing the size of the circuit board. And manufacturing costs can actually then, therefore, go down. I mean, they wouldn't do it if they weren't saving money. It's cheaper and fancier. And that's what you get for the PALs and the CPLDs. We take the next leap to an FPGA, and what you end up with in an FPGA is you take the CPL ID. Again, like I said before, this is the kind of thing you see on all the output pins of an FPGA. But we replace this local array with a very different way of doing things. What happens down here is you got 114 lines that come into this programmable, this local array down here. And as you add more and more inputs, and you want to put more and more of these local arrays on one big chip, okay, and you want to connect them all together, what's going to happen is these start getting bigger and bigger, and this is a scaling problem. All right. Now, it wasn't a problem when you could only make silicon chips so big and all the traces were gigantic. So there's only so much you could put on a piece of silicon. This was, the greatest thing that ever existed at that time. But as you could put more and more in there, you got a scaling problem. So what they did is they changed how these logic cells work, and they use what's called a lookup table instead of these programmable sum of products arrays. All right. But you still have this programmable interconnect in here, this so-called routing that goes around the chip. It's the same idea in here, the chip-wide interconnect. So you can connect all these logic blocks together, and you can connect the logic blocks to the I/O pins and stuff like that using this programmable interconnect. The FPGA is a increasingly flexible and scalable type of a design. So that's the leap you make to an FPGA. And what do we got here? Therefore, what do you get? You got the simple ones. Maybe you can replace 200 gates of TTL chips and stuff like that on a circuit board with one of these simple ones. A complicated one, a complex one, because of its internal routing and the fact that it has multiple SPLDs, you can get on the order of that many individual TTL gates can be replaced. Well, an FPGA Now, mind you, I think this is 20 years old, has on the order of like 1 million TTL gates, can all be in one FPGA. That's why I want to talk about FPGAs. So if you're used to designing, combinational circuits with a bunch of discrete gates, and you want to make bigger and bigger and bigger projects and do cooler and cooler things, and you're running into circuit boards that are, all of a sudden 12 inches square, you might want to make a leap forward. You could probably go over to PLDs, PALs, and reduce a lot of chips down that way. But in terms of cost and just super awesome coolness, I'm going to make the leap all the way up to FPGAs here. And we'll see why as we look at some of these FPGAs, because these things, and to some extent the CPLDs do as well, they have what is commonly called IP blocks in there, which stand for intellectual property, okay? Or, complex devices that are actually inside the FPGA. FPGAs, for example, quite often have RAMs in them, so big memory blocks can be in there. You can implement a memory bit using the gates and the LUTs, as they say, inside of an FPGA, but that's a waste of a LUT because that's a physically large thing in silicon, and it's common to need memory inside a lot of circuits. So they actually, again, that's why we have so many FPGAs. You can buy them that have memory blocks in them. You can buy them that have SPI controllers in them, Ethernet controllers. You can even get them with CPUs inside there. Now, I'm not going to go that far. I want to focus on the simplest FPGAs that I know of because I'm a hobbyist and I want to be able to tinker with these things. And if you're just starting out from ground zero, you do not want to dive into an FPGA that has embedded CPUs and all this other stuff. Let's start at the beginning, okay, and talk about the LUTs and the PLLs, the RAM blocks, and things like that. Those are very common, universally appearing on just about every FPGA I've ever seen have things like that in them. And let's see how to program these and how to use them in our designs. So what do we got here? We've got some kind of differences here. CPLDs, good for random glue logic to replace circuits that were, when you outgrow your PALs. Down here, it means specifically they're saying these are good for combinational circuits. You don't need a lot of flip-flops in your design. It's not a very stateful thing. You're not building state machines. We're not building complicated state machines anyways. You can use a PAL or a CPLD. If you really want to just replace a bunch of TTL gates or something like that, that's what these guys over here, your PALs. And if a huge number of gates, you can use a CPLD to do that sort of thing. If you actually want to build a state machine, if you want to implement something like a UART or a timer or an I2C interface or something like that with the field programmable device, these are kind of too simple to do that. You probably could buy a CPLD that has I2C interfaces and stuff on there, but it's not like it's not common that you would build more complicated stateful things using these chips, is my point. And down here, it's also Dr. Wang's point that they can use various things. What do we got here? DSPs, logic emulation, network components. If you want Ethernet interfaces and stuff like that. In fact, anything that's super high performance today, like 100 gig E and 400 gig E, they're all done using FPGAs on the interfaces, cell phone towers, satellite uplinks, all that stuff. They use DSP math blocks that are inside FPGAs. That is where they're all going. These are the big ones that do that sort of thing are rather costly, but they are incredibly flexible and really useful. And they are reprogrammable, so if the protocols change or something like that, you can, as long as the chip is fast enough, replace the programming in an FPGA with a different one. If you build a simple UART in your FPGA for a project and you decide, I want to use I don't want to use an asynchronous protocol anymore. I want to use a synchronous protocol. Instead, you can redesign the UART, and you don't even have to rebuild your circuit board or anything. You just reprogram the FPGA that's in there now, and it will behave differently, which is super cool. All right, so back to the Wikipedia page. I'm not going to go over all the history and stuff like that, but here's the dates that various things happened in various companies and where these things kind of came from. Eventually, so they were originally PROMs and one-time programmable things, which is why I didn't really get super into the PALs. I've got some, but they're one-time programmable. Right, that's what programmable, but not EPROMs or reprogrammable. And as a hobbyist, you just burn through all these chips, and when they don't work, you throw them away. No, it wasn't so fun for me. These days, you can use a GAL instead of a PAL. Those are made by Lattice Semiconductor, and those are reprogrammable PALs. So if you're really bent on wanting to get the PAL experience, you can get a generic EEPROM programmer these days, and you can program yourself up all the PALs you want, and you can still buy them. They're still in production, but you'll get a GAL instead of, there you go, blah, 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 blah. Somebody was acquired by Lattice over here, and Lattice sells these reprogrammable PALs, and they call them GALs, all right? In fact, hey, there's a Wikipedia note about it. So it uses an E² floating gate, yada, yada, yada. This is an EEPROM type device, okay? And they're pin compatible, I believe, with the PALs. So just don't even waste your time with PALs. As a hobbyist, you want to get these if you want to program on the bottom of the barrel. I've never used the CPLDs. These were popular during a time in my life when I was busy socializing and going to graduate school and things like that, and I didn't use these. When I came back up for air professionally and intellectually, I dove into the FPGAs. So this is where I ended up. So this is where I'm at nowadays. What do they got over here? Remark, these did this and they work like that. I don't know. I'll leave this as a task for the viewer to go and read all the Wikipedia details. Now remember, the whole reason I wanted to go over all this up front here is because I wanted everyone to be on an equal footing and understand what a PLA, a PAL, a CPLD, and an FPGA really are and what the differences are in a general sense, so that you can know and you can choose the right kind of device for the project at hand. Now, I want to focus on FPGAs for a while, and I want to build some cool stuff. I want to make some UARTs and some joystick controllers, maybe a PS2 keyboard controller, things like that. And for me, that's much easier to do with an FPGA than it is with a CPLD. Now, as I said before, on my way out the door here, I want to talk about this handout. I'm putting a link to this below the video on YouTube. This is the notes for a lecture or two that I gave when I taught this topic, Boolean algebra and in the laws of Boolean algebra, in a university course. And in here, I talk about something that I mentioned earlier, all the different notations that everybody use to represent a not function, all right? I use the bar over the variable to mean not. So Q equals a bar, okay? And there's your truth table, there's your gate, and these are all the other notations you'll see that are commonly in use. And I also include the C notations if you're going to write it in a C or C++, Java, all the other languages that are all the same as C, and add random features to them over the years. Use these notations over here. You need to understand that this is all of the above, even across Wikipedia. I find this annoying. The whole reason this handout was created for my students was because I couldn't find anything online where I could point them to that was consistent from page to page. The Wikipedia articles on two very tightly knit subjects use two different notations. So this is a gift to my students and now you, so you can recognize when you're looking at various documentation that you find around the internet, what are all the common notations that you'll see that all really mean a bar, like that, okay? The AND function, I tend to use the wedge, A ended with B like that. The dot works because this looks like multiplication. As I said earlier, here's a truth table. What's 0 times 0? 0 times 1. 1 times 0. 1 times 1. Okay? This is multiplying in base 2. So that's why you see these notations from your common grade school algebra classes. In C, the bitwise operator is a single ampersand. Logical is 2. If you don't know what that is, go read a C book. I can't go. There's only so many deep levels of tangents I can get into in one video. The OR, I use the wedge for the OR, and I use this on purpose because when I talk to my students about Boolean algebra, especially if you want to design a Boolean function that performs binary multiplication on a multi-bit number, we have to differentiate between adding and ORing and multiplying and ANDing. Okay? So I made it a point to always use the wedge for AND and the V for a OR. Okay? You'll see the plus used quite often. And see, it's a single bar for bitwise, double bar for logical. And the C stuff, again, I threw in here because this course, they write a lot of C programs and C++ programs, and I wanted to make sure that the students always knew this. Whether it's relevant in this context or not, I don't know, but this was for a specific purpose for Computer Science 463 at Northern Illinois University. Okay, so what is this adding? If you think about addition in what we call saturated arithmetic, and by saturated I mean once you add 1 to the highest possible value that you can have. If you want to add 1 to this, what might be thought of as infinity, the maximum value that can be stored somewhere. And in a single bit, that would be simply 1. 0 is the smallest value and 1 is the biggest value. If you add 1 to the biggest value in a system that uses saturated math, you stay at that maximum value. You don't overflow and go back to 0, in other words. It's not like an odometer in your car. So, in that sense, this is addition. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0, and so on. 1 plus 1 is 2, but it can't fit, so you put the maximum value in there, and that's 1. That's one way to think of this, okay? So that's one of the reasons you can see that the plus is used in some contexts for the OR function, all right? Now, I talk about other ones in here as well that are really composites of other things. What is an exclusive OR? Well, it's this function, right? And there's the truth table for it and some other things. For completeness, this is every possible Boolean function that can be performed with 2 inputs. There's 16 possible outputs because you have 4 different combos, and 2 to the 4th power is 16. This is every one of them. All right? This is useful in this context because when we talk about an FPGA and its lookup tables, that's what we're storing in the lookup tables. We're storing whatever function we want. We don't have a sum of products. We don't have all the gates in there like you do in a CPLD and a PLA or a PAL. What you do is you have a little teeny memory and you store these 4 bits in there. And you use this as an address. You simply say, give me the whatever's on line 0. Well, that's this one. Give me what's on line 1, line 2, line 3. If all I wanted was a bar with 2 inputs, which is kind of a weird function if you think about it, that's what you'd store in that memory. If I wanted an XOR, I would store this in there and so on. This is how you program an FPGA. What you're doing is you're creating the values that are stored in what we call a lookup table or a LUT. So we'll come back and talk more about this later. De Morgan's laws are necessary. You'll see about that in my other lecture. I don't want to go into it right now. There's a notion of completeness. This is Boolean algebra stuff, great things to ask students about on quizzes and tests. Operator precedence and things like that. Where do you put the parentheses and algebra, blah, blah, blah. A link to a Wikipedia page with a wonderfully inconsistent use of the ands and the ors. Not on any one page, I will say. But if you click around in there and go from one to another, you'll see they're using different notations. Or at least they did in 2019 when I first decided that I needed to standardize them for this handout. And then, of course, the basic functions that you have in this guy called De Morgan, which is useful when we look at this. Okay, sum of products. That's why we're on this handout, people. Now, I'll leave it to the other lecture, but the short of it is this. No matter what Boolean function you ever want to express, you can express it in sum of products form. And I talk about it in this handout, and I talk about it in this video. So if you have a function that looks like this, how do you express that, right? Here's your truth table, here's your output, here's what all the steps, and I go through how this all works and why, no matter what you do, you can always express a combinational function in sum of products notation. And the reason this is important to us right now is because a PAL and a PLA and a CPLD that have all these sum of products arrays in there, you can always implement any function you want. You're not limited, okay? And this is why, because of how this works. You'll have to watch the other recording for that. There's another thing called product of sums, which is the mirror image of sum of products, which can be proven to be the same thing by way of De Morgan's laws and how these things work. I talk about that in the other recording as well. And if you are designing with discrete gates, you want to choose when you're going to use one over the other, and it's actually pretty simple, but it doesn't matter if you're building a generic device. This is, whatever. This might be of interest to you, but not so much important to our case, because the chips are always built using sum of products forms. I then talk about, if you want to use discrete gates and things like that, how do you reduce the algebra and stuff like that. Again, links to the detailed walkthrough of this in the description below. What I wanted you to see for this point right now was how the sum of products works, and understand and know that it is here. If you are confused, you can always go to the Wikipedia page or look at the other recordings that I have posted. Now, in the bottom of the Wikipedia page, it talks about how they retain their configuration. Okay? Some of the differences between the CPLDs and the FPGAs and the PALs and stuff like that have to do with how you program them and how it remembers what its program is. Okay? Now, some of these things, like there's a picture one here that has a UV erasable EEPROM in there. Some of them all have an electrically erasable PROM in them. Now, buried in here somewhere, it'll probably talk about the fact that FPGAs, as a general rule, have a little external EEPROM, a little flash PROM. As of 2005, most of these are this way. They don't talk about FPGAs in here, I guess. But the CPLDs and the PALs tend to have their own programming, little flash ROMs or an EEPROM or fusible link ROM, one-time programmable, all that other stuff, all inside the package. While FPGAs tend to have a little teeny external EEPROM chip that sits next to the FPGA that you have to program, and the FPGA, when it powers up, will download a configuration file from that little EEPROM. So, and that's what we're going to see when we program ours. Then they talk about the programming languages for PLDs. And they have a whole link here for FPGAs. You can go here and look at these. And the usual big boys, Altera and Xilinx, used to be separate companies. Altera is now owned by Intel. Xilinx is now owned by AMD. So, although these brand names are still widely used, I think they'll slowly erode away, maybe, and be replaced by, Intel and AMD. But for now, these are still the big boys in town. Now, I'm going to use a Lattice chip on a project that I want to talk about and focus in here, simply because they're very simple and they're attainable, they're understandable. And a first-time FPGA user can actually fully understand the whole device. As you get more complicated, you end up with a lot of real gray areas, and things get more complicated when it comes to programming them. So I want to focus on the basics and build up from there. I'll leave it to you to figure out how to use embedded CPUs and giant IDEs with click and point user interfaces and all that other stuff, which are great, by the way. But if you start with those, you'll never know what's going on under the covers, and you may actually have trouble getting things to work, because no matter what happens, you're always kind of left with, and then you have to connect it to custom logic sort of things, which means you need to know the basics. Now, what do we got in here? Timelines, gates up to like 9,000, 1987, yeah. So in the 80s, yeah, 9,000 gates. We're starting. I'm going to use a lattice chip that has about 8,000 gates in it. So those of you liking retro, we're still in the 80s. But as you start getting more complicated in the recent year, look at 50 million. In 2013, I think they have a billion. I thought I saw an announcement of a 1 billion LUT chip. I don't know if it was from Xilinx or Altera, but yeah, it's just insane. And what's the demand like? Oh, it's enormous demand for these chips. These are a big deal, all right? Like I said, anything big, any routers, you go work for Cisco or something like that, there's not an Ethernet. No. It's all FPGA on those boards. Take one apart, look inside, you're going to see FPGAs everywhere in there. And this might look a little bit familiar to the CPL diagram. There's the output of this thing has this flip-flop, and same kind of a thing in here, the multiplexed output. And they don't show this loopback line because a LUT is a single tiny little circuit, where the PAL had all those gazillion AND gates in there. One of these logic cells on an FPGA focuses very much so on these LUTs, okay? The output, if you wanted to feed it back around to the input, you use the routing network to do that. So in a way, FPGAs are actually simpler than CPLDs and PALs, because they kind of shrank down the meaning of one of these logic cells, and they increase the number of them that are in there, and the interconnection, the so-called routing fabric and stuff like that, okay? So, and here they talk about soft cores and CPUs that are inside the FPGAs. What else do we got in here? Oh, yes, clocking. We'll talk a lot about clocking. This is a big deal with FPGAs. How does it know when to do what it's supposed to do and things like that? And how do we avoid metastability? Okay. Yes, that'll be a whole video on its own. And what a 3D architecture. Oh, this is just fabrication, how they're made. If you're into the physical nature of how the silicon is put into a chip, we're getting fancier, is what that means to me. And eventually we come down here to how they program these things. And as they say, you use a hardware description language. And there's two of them. One of them is called VHDL, and the other one is called Verilog. Now, I learned Verilog. Here's the two right there. I learned Verilog because when I was trying to figure out how to program an FPGA, a lot of the books that I found available were kind of confusing to me, and we'll talk about that a little bit later in another video. So what I did is I went around to various universities, and I found that MIT, CMU, and Stanford posted their course material online. And I mean, this is, I don't know, 12, 15 years ago or so. And they all used Verilog as their language in the classroom. So I learned Verilog. These two are so interchangeable now that every single module, as you'll see, we call them, in any project that you create, certainly in the Xilinx IDE environments, can be written in either language and interconnected at will, willy-nilly. These are very compatible with each other. I'm going to be talking about Verilog, okay? If you're outside the U.S., you may see more in VHDL. The U.S. military also uses VHDL, but a lot of academia in the U.S. use Verilog. So you're going to have to pick one, and I'm going to pick Verilog because that's what I know. There's another reason to pick Verilog as well. There are open source and free tools that are based in Verilog that are the price is right. Okay? So that's what I'm going to use for the example programs that I'm going to talk about in here because simply we have the tools to compile Verilog programs. And a major aspect of writing software for FPGAs is to make sure you can simulate them. And there's a lot of tools that people have put together over the years that allow you to simulate programs in Verilog. I am sure they exist in VHDL as well. Certainly the the Xilinx and the Altera tools will do both without any problem. But the free stuff that I'm aware of is focusing on Verilog these days. So I'm going to go that route. You can see the clock on the wall suggests that we're running out of time. So this is, I think, a pretty reasonable place to stop. Next time we'll look more closely at a chip from Lattice in the HX series of chips, the ICE40 HX FPGA. These things are super simple. They're still in full production. They're very inexpensive, relatively speaking. I think last time I bought one, it was $6. I think with all the inflation right now, they might be up to $9 with the COVID shortage and all. They're available up to 7,680 LUTs. And that should give us more than enough to get us in trouble and have some fun. See you next time.